This is going to be then the first an introductory talk on the methods and yoga related to topological complexity. And well, I attempt to make a more or less comprehensive description of the methods. This topic has had a lot of recent developments and very interesting connections to both to theory and applications. And well, I'm going to be focusing basically on the first two topics, namely giving only motivation and basic results, following basically the original work of Michael Farber. And then I'm going to be talking about variants of this concept. I'm going to be describing several modifications of this concept, which are either motivated by applications or which are interesting by themselves. And since it's going to be basically impossible to review the rest of the topics, which include some things about differential geometry, homotopy theory, and then some more homotopy theory in rational methods, a stochastic point of view, and some computer implementations. This is going to be very difficult to review. So what I will do is, at the same time that I speak of the variants of TC, I will be introducing some of the connections with several of these concepts. Okay. So here's the basic definition. Let me start with the basic definition. So X is supposed to be a topological space. Then you look at the space of free paths, on base paths on X. And then the key point to look at is this map, going from the space of paths on X down to X times X. And this is just the endpoints evaluation map. It sends a path gamma into gamma 0 and gamma 1. This is essentially the original idea of Michael, and then you define the topological complexity of this space to be the sectional category of E01, of this double evaluation map. Now let me just make a comment here. I'm reducing, well, what is the sectional category of a map, for that matter, the sectional category of a map F from X into Y is by definition the minimal number of open sets that cover the base space of the map, the range space, so that in each of these open sets you have a homotopy section. Now I'm going to be using the reduced version of this definition. I'm not counting the number of open sets covering the range space. I'm counting one less than that. This is what is called the reduced sectional category of the map. And the other variation that I'm making, I guess, from the standard point of view, is that I said, as I said, on each of the open sets of the covering, you're required to have a section up to homotopy, namely a map going from UI into X, so that this diagram is only commutative, only up to homotopy. So as a consequence, this is a Farber homotopy invariant, namely if X is changes by another space which has the same homotopy type of X, and the homotopy equivalence between X and X prime is compatible with the projection, then you would have essentially the same definition just because of what I said. Okay, so the motivation for such a result, the original motivation for such a result, is that in the case of the vibration of the map that I described, the double evaluation map, well, essentially you think of X as rising as the space of states of some robot. For instance, think of this planar arm with 4 revolving planar nodes, so that a state of this space is characterized by giving you 4 angles, planar angles. So essentially the configuration space of that robot arm would be a subspace, maybe the whole space, given by the Cartesian product of 4 copies of the circle. Each of the factors accounting for each one of the angles in here. And the idea, of course, is that if you look at the Cartesian product x times x, This is thought of as being the space of the motion tasks of the robot. And then the space of paths will be the actions that the robot has to perform, and specifying a motion planner would just be a rule that assigns to each task an action of the robot, so that the composition, when the robot applies this action, solves this task, this motion task. So this is essentially the motivation, and here's some it works. And here is some notation, some convenient notation. The system of open sets and local sections is going to be called the motion planner. One such motion planner. And each of the UIs will be one of the local domains of the motion planner, and each section will be called a local rule for this motion planner. Okay, now in applications, essentially, one of the actors, the main actors in motion planning is the presence of noise. This is something that we cannot avoid in real life, and we have to learn how to deal with. And well, taking control of the noise is naturally included in this model because sections are required to be continuous. Implicitly, we are in the category of topological spaces, so sections are continuous, which means that small perturbations of the task to solve only result on small perturbations of the action to apply for solving this task. So, in a sense, one calls these continuous sections just robust to noise motion planners. And the idea, of course, is to avoid accidents. If you have a robust to noise local section, motion planner would mean that essentially you can control the presence of noise in some way. If you have a good control of the noise, then you would have a good control on the actions to apply for solving the tasks. Alright, now the bad news is that a motion planner with a single local rule can hold only precisely and only when the space is contractible, only when X is contractible. Well, I'm going to be using this, although people in the back might not be able to see it. It's simpler here. Only when the space is contractible. And here is essentially, this is very simple. Namely, if the space is contractible, then you can go from each point to another point just by first letting the space go, contracting itself, and then running back the contraction. So you go from one point contracting to the other point. And on the other hand, if you can plan the motion from any point x into some fixed point x0, at least if you can plan the motion from x into y, then you can plan the motion from x into some fixed point, and then that essentially gives you the contraction of the space. So this is why then you have to, you ask for the sectional category, namely the minimal number of open sets covering this space so that there is a local section, continuous local section on each of one. And that accounts for describing optimal motion planners, namely motion planners, systems of local domains and local rules, so that that's the minimal number in which you can cover the space. One of those I'll call an optimal motion planner. And here's an example. Suppose this is your space of tasks, the Cartesian product of x with itself. And that you have here, suppose this is the partition, the covering, the open covering coming from some motion planner. And of course, I'm assuming that on each of these pieces one has some local rule. Now look at the dot in the yellow dot, and in the presence of noise, this would be a task which, if it is moved a little bit in the presence of noise, one would not be sure whether I have to apply the local rule coming from the right-hand side or the other local rule. So I will say that this task has instability order of 2. and this one would have instability order of 4. And of course, this is the possibility of having an accident because of the presence of noise. So you would like to define the instability of the motion planar to be the maximal of the instabilities of each of the tasks. How dangerous might be, how the dangers could be solving the motion planning with this motion planning with this motion planner. So this actually is a measure for minimizing the possibility of accidents. And one could actually define the topological complexity in terms of this notion by minimizing the instability of motion planars, namely taking a motion planar with the least possible chance of having an accident. And a basic result of Farber is that the two numbers agree if the space is nice enough and Euclidean neighborhood retract. And as a consequence, optimal motion planars would be safe, namely would have the minimal possible order of instability. So that says that topological complexity has some sort of local flavor, as it is describing here, because notice that this open cover can be fixed somehow. For instance, if you remove that point with 4 possibilities, you remove it and introduce a new local rule, a new local domain here, so that you would have now 4 possible dangerous situations, but of order instability 3. So that would what you would be doing by considering this thing. But the thing is that the two things agree. So here's the point. In theory, it's very interesting to try to compute this invariant. This is a homotopy invariant. This invariant of the space of X, and actually understanding general properties of TC of a space. But on the other side, if you are more interested in applications, then it might actually be more interesting describing optimal motion planners, or at least safe motion planners, even if they have many local domains. And actually I'm going to be talking about both points of view. Okay, so let me start with some basic general properties of this concept. The first thing to notice is that double evaluation map is a fibration, and that's because what you do is just essentially, if you take a path, then you just restrict it to the endpoints. And the point is that this restriction is a cofibration, so it's a standard exercise that then the map induced by applying this functor of maps of something into X, then transforms cofibrations into fibrations. So, and the point of mentioning that is that you can define the topological complexity in terms of local sections, not up to homotopy, but strict sections. Because if you have a homotopy section, because of the homotopy lifting property of fibrations, you can just fix it to get a honest section. Okay, now the other thing I already mentioned, that this is a homotopy, a fiber homotopy invariant of this map, and it is interesting to notice that the path space on X has a homotopy type of X. And the double evaluation map has a homotopy type of the diagonal. Namely, if you have a path in X, if you have a path, then you can just collapse it, say, to the middle point. That would be just your homotopy equivalence from the space of paths to X. And that's compatible with the evaluation in one of the directions. So, since it is a fiber homotopy invariant, TC can be defined as the sectional category of the diagonal map. And as a consequence, TC is a homotopy invariant. I already said it, but here it is. It's a homotopy invariant of X. And it actually something more general holds, namely if Y dominates X up to homotopy, which means that you have a couple of maps of this sort, so that the composite is not the identity, probably it's not the identity, so probably X is not a retract of Y, but it is up to homotopy. So if Y dominates X, then it also, the topological complexity of Y dominates that of X. And the reason is actually very simple, given the definition that I've given, which says, okay, here you have the situation, the double evaluation map for Y, for X, and for X. And so I want to see that if I have a system, a motion planner of Y, I can induce a corresponding motion planner on X with at most that number of local rules. And for each such local rule for Y, what I can do is just take the pullback of U under this thing, namely the inverse image. If these U's cover this space, then these sets will be, of course, open and will cover that one. And then I would need a section from here to here. And what I can do is, well, I have no obvious way of lifting here to here because this is not a pullback. But what I could do is just travel here, then go up, and then apply this map. And that composite, when you follow it with the projection, then, because of the commutativity of the diagram, will only be the inclusion followed by this composition, which is homotopic to the identity. So you get here then that composite, indeed a local section up to homotopy. And then if you need it, you can just fix it. So spaces dominating up to homotopy, smaller spaces, have larger topological complexity. Now there is a close relative to TC. TC is just a special case of sectional category of a certain map. And in particular, one can look at the LS category of a space, Snyderman category. And well, a way to define it is as the sectional category of the inclusion of a point on X. Suppose X is path connected, so it doesn't really matter which point you choose. So by definition, this is this minimal number of open sets covering X, so that the inclusion lives through a point up to homotopy. That only means that inclusion is null homotopic. In other words of saying this is, you look at the minimal number of homotopy points covering X. That's just the LS category of the space. And a basic result from the 30s, I guess, 30s, 40s, in the 30s, is that this is a really interesting invariant coming in other guises, and in particular it gives a lower bound for the number, when X is a manifold, a closed smooth manifold, then the category of that manifold would be a lower bound for the possible number of critical points of any smooth map defined on the space with real values. The smooth map is supposed to have real values. Now, a very naive question would be, well, TC and CAD are related, are close friends, and CAD has this very nice property of in differential topology, geometry. So there should be some kind of connection between some similar property for TC. And well, I don't know such a connection on the nose, but I will be describing some interpretations with some geometrical meaning for TC. Now, well, I introduced CAD because in terms of that invariant, one can give operand estimates from below and from above for the topological complexity of a space. And the thing is that the topological complexity of a space X is bounded from below by the category of X and from above by the category of the Cartesian product. And this is a very handy diagram to keep in mind. And for instance, this inequality follows just because if you take the double evaluation map and restrict it through this section, namely here you fix a point and you send X into this fixed point, comma X, so you're just sectioning it at the level point here, then the pullback of this thing, namely those paths that its end and its beginning and its end land actually here, coincide with those paths actually that start in a fixed point. So the pullback of this is just the space of base paths which are based at the beginning. So just paths that start in a given point and then just go everywhere they want. And of course this space is contractible because you can just shrink every path to a point, and that would tell you that if you have local sections, you can just pull them back here, and that would give you essentially this inequality. The other is also very useful to have in mind for other kind of applications. Namely, if you want, I want to say that if I have a local section for the map defining category of a Cartesian product, then I can define a local section for this, and that just comes from this other diagram. Namely, consider the base space which is contractible, the space of base paths on x times x. What is a path on the Cartesian product? Well, it has two components, so these are two paths. These are really two paths. This is the Cartesian product of paths. It is, of course, contractible, but in terms of that, if you have such a pair of paths, what you could do is just run the first one backwards and then just keep on going with the first one. And so consider that one, and that makes this diagram commutative, if you think of it just for a moment. And that means that if you have a section for this, local section for this vibration, then you just can continue it with this inclusion, and you will get a local section for the other vibration. And that will give the other inequality. Okay, the other basic property that I want to mention is that the topological complexity of a topological group is actually nothing new. It's just a category of topological group, and this actually holds in more general terms. Namely, this is true for any Hopf space, not necessarily associative, and this is a result of Scherer and Lupton. This is useful to keep in mind because later on I will be talking about topological complexity of H spaces or groups and stuff like that. Well, a slightly more interesting way of estimating this invariant is in terms of cohomological information as well as in terms of homotopical information. On the right hand side I have here the upper bound, which is twice the homotopy dimension of x divided by the 1 plus the connectivity of the space. So what is h dim of x? This is just the homotopy dimension. This is the dimension of the smallest CW complex having the homotopy type of x. And I call the start of x the first dimension when x has homotopy information, namely the first dimension where the corresponding homotopy group of x is non-trivial. The first not negative dimension. And on the other side, I have essentially what is called the zero-cup length of x, say with respect to some cohomology theory. This can be some generalized cohomology theory. It could actually have twisted coefficients if you want. And it is defined essentially as follows. It's defined here. So you define first what is the concept of a zero divisor. A zero divisor is some element in the cohomology of the Cartesian product. That would be a zero divisor if, when I restrict it under the diagonal, it goes to 0. The reason for the name of a zero divisor is that usually the cohomology, well, if you have the Q-net formula, or at least you have a way of mapping the cohomology of x times tensor the cohomology of x into the cohomology of the Cartesian product, just by exterior multiplication, if your cohomology theory has products. And by definition, when you restrict it with the diagonal, you will get essentially the multiplication. And if it goes to 0, then that would mean that you have a pair of zero divisors. Well, having defined then what a zero divisor is, you look at the largest possible number of such elements whose product is non-trivial in this ring. Now, that's a definition for this lower bound. And, well, the upper bound essentially uses obstruction theory, namely twice the homotopy dimension divided by the start of the space. That uses essentially obstruction theory. Namely, you can transform the multi-sectioning problem into a mono-sectioning problem and then construct this global section skeleton by skeleton. And each time you want to go one stage in the next skeleton, essentially you find some obstruction that you want to see that it is non-trivial. And of course, this is a very difficult thing because analyzing some obstruction depends on analyzing all the previous ones. And even if you find at some point some non-zero, some zero obstruction, meaning that you can extend your section to the next level, you might be not lucky and might be choosing as an extension that will not extend any further. So eventually you would have to go back and rearrange the lifting, the partial lifting. And that is, the name for that is that in dealing with obstruction theory, you have to deal with indeterminacies. And this is a very difficult and sometimes inaccessible problem to deal with when using this. Now, the good thing is that the upper bound that I gave indeed uses obstruction theory, but it is for free. Basically, that upper bound corresponds to the case where all possible obstructions lie in trivial cohomology groups, just by definition, just by dimensional reasons. So this is the one that is easy. That's that upper bound. Yeah, this one. And on the other hand, what I didn't say is that the cohomological lower bound is rather accessible. You can do, for instance, suppose you take singular cohomology, then the cohomology ring of X with, if X is a CW complex, then it's workable in most cases. Okay, so that's pretty much about these estimates. Proving the lower estimate is rather easy, actually. Namely, if this is more general, suppose you want to estimate from below, bound from below the sectional category of any map, for that matter. A map from X into Y. And the point is that this will always be bounded from below by the cup length of elements in the kernel of the map induced by F in cohomology. And the reason for that is, well, suppose I'm looking at sectional category. So I have a bunch of open sets covering Y with corresponding local sections. On the other hand, I want to compare this number of open sets with elements in the kernel of the map inducing cohomology by F. So suppose you have such elements. Now the point is that there cannot be many of these elements with a non-trivial product, because being these elements in the kernel, then you can just restrict it under S, which would be just the same as restricting Ki under the inclusion. And since it goes to 0 here, it would also go to 0 when restricted to Ui. So this guy goes to 0 and therefore comes from a relative cohomology class. And therefore the product of these guys would come from the product of the relative elements. And that product, because of the way that the product behaves, has indeterminacy, and determinacy is the union of the indeterminacies of the partial factors. And if the partial factors cover the whole thing, the product of the relative classes would have to be 0, because it would have to lie in the cohomology of Y, Y. So there cannot be many of these compared with the number of these guys, and that essentially accounts for this inequality. Okay, so with this technology, I can describe some examples, some standard examples, namely, suppose I take the complex projective space of dimension M. Well, it's well known that the singular cohomology, say, with integral coefficients, is a polynomial ring on a variable of dimension 2 and height n plus 1, depending on how you want to count the height. Then the cohomology of the Cartesian product, because of QNF's isomorphisms, is just the tensor product of the whole two things. It's a polynomial ring on two variables with the corresponding heights. And one notices that this difference would be a zero divisor. Namely, if I multiply x2 times 1 is x2, and then I would be subtracting the same thing. That goes to 0 on the diagonal. So that's a zero divisor. And the 2m power of that element is non-zero. Essentially because of the heights. This would have the usual formula, and you cannot take powers of x2 larger than m, because they would be 0 here. And the same here, so the only really factor that appears here is up to a coefficient, a binomial coefficient, would be that one, but that's precisely the top class times some integer number. So the point is that that's non-zero, and because of the lower bound that tells us that the topological complexity of this space is bounded from below by the number of factors, namely 2n. On the other hand, well, we know that the complex projective space has a cell structure with a cell in every dimension which is even, and up to 2n. So up to 2m. So the dimension is precisely 2n. This is a simply connected space. It starts in dimension 2, and if you apply the formula, you will get that the topological complexity is also bounded from above by the same number, so one gets that for free the answer. By the way, this argument works just the same, not only for CPM, but also for any symplectic closed, simply connected manifold. Essentially, the role of x2 would be played in that case, in that general case, by the role of the cohomology class determined by the two-form, the closed, non-degenerate two-form corresponding to the structure of the symplectic manifold. All right. By the way, similar considerations tells you that the category of CPM is M, the category of the Cartesian product is 2M, and in particular, that these are the same answers. So the topological complexity of CPM is precisely the upper bound coming from the estimates, the category of the Cartesian product. So in a sense, simply connected manifolds behave completely different from, say, Hopf spaces, for which, for the later, the answer for the topological complexity of Hopf spaces, of topological groups, say, is just category of the category of the space, and in this case is twice the category. So they behave completely differently. Now, it is interesting to notice that the same thing, you can do the same yoga, the same exercise with spheres, and you will find that the lower and upper bound agree for even spheres, but for odd dimensional spheres, the lower bound would only be 1, whereas the upper bound would be 2, and so you need more to decide what this value is. And there is a reason for this failure. And by the way, this comes from just anti-commutativity, because the generator of the odd dimensional spheres, of course, the fundamental class is odd dimensional. And that the reason really, what this is telling you is that, well, the answer is that the topological complexity of odd dimensional spheres is actually 1. So there was a real reason for this. And in order to do that, well, you can apply some more elaborated obstruction theory argument, or more simply, just construct an optimal motion planner with 2 sections. And that's given just as follows. You can cover the odd sphere cross itself by these 2 open sets, namely pairs of points in the first case where they are not antipodal, and the second case where they are not equal. Now I have to plan the motion in a continuous way in each case. And if I have 2 points that are not antipodal, then I have one unique shortest geodesic, and I can use it for planning the motion. And that would be just the section that I need here. And in this case, I need to plan the motion from x to y when they are not the same. If they are not the same, then x is not antipodal to minus y. And what I can do is, say I travel from x to minus x, using the fact that the sphere is up, and so I have a non-vanishing, never vanishing vector field on the sphere. So following the direction of this vector field, I can go from x to minus x, and then because the points are different, these are not antipodal, and then I can just use a geodesic for traveling from x, minus x into y. Alright, so that was the original argument for this, because it's of course much simpler. Now, another cute interpretation for one of the properties for TC is the following. What happens when you want to plan the motion of two or more robots at the same time? So the basic result here is that if you have a couple of maps, F1 and F2 going correspondingly from xi into yi, then I can form the Cartesian product of the two maps, and there is a general result that the sectional category of the Cartesian product of the two maps is bounded from above by the sectional category of the factors, by the sum of the sectional categories of the factors, under nice topological conditions on the base space. And I'm going to be describing very quickly a proof of this. It's quite easy to see, but let me apply it in the following example. For instance, take the Cartesian product of the double evaluation map for y and for x, or the double evaluation map for the Cartesian product. Again, a path in the Cartesian product is a pair of paths, so you have a pair of paths. And the evaluation map here takes the first map and the second map evaluated at 0, 0, and then 1, 1. But notice that this space is the same as this space as soon as you swap these two factors. And you would, originally you evaluate at 0, 0, and 1, 1, and 1. And if you swap these two factors, you would be evaluating at 0, 1 when this comes into here, and 0, 1 when the y goes to the other side. In other words, this diagram commutes, and you get for free from this lemma these results when you apply the definitions, that the topological complexity of a Cartesian product then is bounded from above by the sum of the topological complexities under nice topological assumptions. Okay, as I said, the interpretation here is, well, if x is the space of states of some robot, x1 and x2 correspondingly, then you can just have the two robots do their business at the same time, and a position of those would be just a pair of a position of the first factor, comma, a position of the second robot I meant. So essentially the Cartesian product of spaces, which are correspondingly the space of states of some robot, is just the space of states of the system of the robots which are functioning at the same time. I'm not worrying about the possibility that the robots could collide. They could if they wanted, and that has no implication. It's an idealistic example. Now here's an interesting exercise for you. Find a couple of spaces, x1 and x2, so that this inequality is actually strict. And well, the hint is look at what happened for category, and namely look at Moore spaces, and the situation is simpler if they are suspended Moore spaces, and but they correspond to spaces of different torsions. Then you can prove that this inequality holds. Another interpretation is if you have a mechanical arm, and you have a mechanical arm with many nodes. Each node can revolve around a sphere of some dimension, so that the space of states of this robot would be determined by a tuple of angles, spherical angles. So the space of states of this mechanical robot would be just a Cartesian product of spheres. In the case, again, where the robot is free to move, no partial arm will collide with another partial arm. So there are no restrictions. Later in this talk, I will be mentioning what happened if you put some more realistic restrictions. Now you can play a little bit with the estimates that I already told you to realize that the topological complexity of the space of states of this robot is precisely the sum of the topological complexities, because it's bounded from above and below by the same number. So here's an example then where this doesn't happen, when you have spheres. And spheres are, of course, very, very nice. Not easy, but nice. Here's a proof of this technical lemma by Schwartz, namely that if you have two maps and you look at the product, then the sectional category of this is bounded from above by the sum of the categories of the two maps. And the idea is, well, suppose the category of this is, the sectional category of this map is n, so you have your n+1 open covers with homotopy sections, and the same here with value m, and you have your sectional, your local sections of the homotopy. Then what you could do is, well, take the whole factor, the whole second factor, and cross it only with each one of these guys. Well, that's an open set here. It doesn't have necessarily a section, but if you do the same thing on the other side, take the whole thing, crossed with each one of the other open sets, then notice that the intersection of these, namely this, that would have a local section, because each factor has a section on each of the u and v's. Okay, so this is the situation that I want to put as a sublemma. Suppose you have a map and you have two coverings, namely this and this. You have two coverings, y by n+1 c's, open coverings, and 1 by n+1 d's, so that in each intersection you have a homotopy local section. Then I want to convince you that the sectional category of the map is bounded from above by n plus m. Notice that you already have a covering, the collection of these intersections certainly cover, but they have too many. They are too many. They are essentially n+1 times n+1, I'm missing a 1 there, minus 1, if you make the counting. So I want really to improve this big number by n plus m, essentially. The idea is, recall that I had, here it is, I had my upper covering, I have the open covering of the C's, and think of the C's as covering the space vertically. Here's one C, here's another C, here's another C. And think of the D's horizontally. Here's one D, here's another D, and here's another D. Okay. Now I can think of the intersections and I get these, essentially these diagrams. On each of these squares I have a local section, and of course I have too many local sections. But the idea is I want to make a trick so that each of the squares in one diagonal can be mixed. And well, let me do the detail in a very special, simple case, but nevertheless is representative. Namely, suppose that m and n are 1 each. So I have only one guy here covering the base space, and one guy here, one guy here. Now, I'm supposing that the base space is topologically nice. And what I need is, this is an open covering of vertical spaces, and this is an open covering of horizontal spaces. And each of them I'm going to be shrinking it twice. I'm going to take another cover so that the closure of this is contained here and the closure of this is contained here. This is something from general topology that you can do under nice conditions. And then again do the same thing, shrink this covering a little bit more so that these conditions hold, and the same over here. Now, look at this situation. Here I have the C0, C1, D0, D1, and I want to take these as part of one thing, these two as part of the other thing, and this and the other one. So the idea is essentially to mix these two. And I'm going to be doing this here. One thing that I should mention is, this is the zero level cover. The upper subscript is just the zero level. And they have the first and the second, the zeroth and the first. This is the first level, and this is the second level. Each one is smaller than the previous one. And the same here. Now, take this guy as your first local cover, your first local domain. Do nothing at the 0 level, the 0, 0, this guy. Then, take these two guys, but shrink it a little bit, and removing this technical part, which is the closure of this guy, the 0, 0 at the level 1. This would be an open set because I'm removing a closed set. And do the same thing here for this guy at the second level, removing the closures of the analogs of the 0, 1 and 1, 0 parts, these two parts, at the level 2. These are open sets, just by definition. And notice, I want to see that they cover. And this is quite easy because, well, notice that the first one takes into account these guys. This is by definition. Now, what about the union, namely these two guys? When I subtract that, well, if I subtract that, but then add this, recall that this is a bit larger than this just because of these conditions. So if I remove this, but I add this, I will be winning. At least I have this much. I haven't really taken out anything because I'm going to be putting this. So what I'm saying is the union of these two guys are guaranteed to contain these two pieces here at the level 1. And something similar happens here. If I remove this but include this, then I'm really including these guys that I already said. So I'm not really removing anything from this, and now the union of the three things contains that, and that, and that. And in particular contains the 4 pieces at the level 2, and those certainly cover. And the key point now is that, well, I have here one local domain, I have a local section there, another local section here, but I want to combine these two. And namely, I want to take the union of I want to take the union of these two things, namely, take this part, but I subtracted this, and take this part, but I subtracted this, which is what I define here. I already said that this is a covering, but what happens? Notice that this is the union of these two things, but it's a disjoint union. Namely, the intersection what happens? What's the intersection of these two things? The intersection of these two things, I claim that it's containing here. So I'm removing the intersection. Because if you intersect these two guys, by definitions, these are at the level 1, the intersection of the 0 and 1 pieces, and the intersection of 1 and 0 pieces, and I can just keep on, I can just keep this piece and this piece. So this is containing here, which by definition is that, and which is, let's see, is evidently contained in its closure. So in the intersection of these two guys is contained in what I'm removing. So by removing this, I'm making the two pieces disjoint, and in each one I have a local section, and then I can combine them because they are topologically disjoint. Alright, so a little bit of point-set topology here. Now let me say some more interesting things. Can I conjecture? One of the, like 15 years ago, it was a hot topic, this thing, because, well, I just said that the topological complexity of a product, of a Cartesian product, is bounded from above by the sum of the topological complexity of the factors. And the same proof essentially applies, well, I gave it Schwarz's lemma, and the same thing applies in general, for instance, for these other type of vibrations. So the category of a Cartesian product is bounded from above by the sum of the categories of the two factors. So far, so good. Now, again, if you look at moves, for instance, you can see that these, of different torsions, you can see that this can be strict inequality. And, Moore factors of different torsions, of course, have different torsions, relatively prime torsions. And, Gamma I guess in the 70s, or 60s maybe, made a list of problems in that time, and he asked, among other things, whether this could be, in the case of a sphere which has no torsion, it's really nice because it has no torsion, well, you have this inequality, and I guess after looking for some examples, he didn't find, people didn't know of examples where this was a strict inequality, and he asked whether this could be an equality for all spaces when crossed with a sphere. And it turns out that it is true in many cases. For instance, in the rational situation for simply connected spaces, by work of Jezus and Hess, I guess that's the way it is, not sure about the pronunciation of that last name. It is also true for a large class of manifolds, and that's work also of Singoff, Rudiek, and Strom. But it fails in a subtle manner, in a subtle way, in general. And actually, in order to find out a counterexample, you really have to do it by hand. You have to go to the tailor and make a suit to your measurement. So it's really very nice. The idea essentially is, well, the counterexample is a space X with two cells. It's a two-cell complex. And it's well known that the category of a bottom cell by itself is 1. And it's also known that the category can increase at most by 1 when you attach a cell. And actually there is an obstruction for deciding whether it increases or not. And you can manufacture a space for which that obstruction is non-zero. But then when you cross the whole situation with a sphere, you have again a top-dimensional sphere, a cell, whose obstruction now would turn out to be a suspension of the previous obstruction. And that example was cooked so that the suspension of that obstruction vanishes. And that essentially gives you the counterexample. That's roughly the way it works. Now, one could ask the same question for DC, whether there is a Gaussian conjecture, which turned to be false in the category setting. Namely, we know that the topological complexity of a product is bounded from above in this way. And now, I already mentioned that the topological complexity of the spheres is just a tiny bit more interesting than their category. Namely, it sometimes is 1, depending on the parity of the sphere, or could be 2. And the question is whether this could be an equality. Namely, the topological complexity of this product being the topological complexity of X plus either 1 or 2, depending on the dimension of the sphere. And, well, it's been proved that it fails in general. Namely, you can cook up this space. This is really an example of Mark, for which the upper estimate coming from the homotopical dimension at the start of the space really gives you the real answer. Topological complexity of that space is 4, but when you cross it with an even sphere, it increases only by 1, even though the topological complexity of even spheres is 2. And the way that this is proved is essentially following the lead of Iguase, but it is not a straightforward generalization. You really have to do some interesting work, but the theory can be set up, and in particular you can get this result. And all right, but actually I guess this situation is just beginning because, well, an open problem is what happens. This is a very particular case in which the topological dimension of the product with the sphere just increased 1, not 2, as expected because of the sphere was even. But can we cook up another example where the topological complexity of a space does not go up at all when crossing with a sphere? And that's, I guess, open. Is it possible to find an example of a space so that one has this equality? For instance, in the case when n would be 2, that would mean that this thing does not go 2, not only 1, but it just stays the same thing. By the way, this number cannot be lower than the topological complexity of X, just because X is a retract of the Cartesian product. Now, Somehow, the interesting thing starts now. I'm going to be presenting things in the way motivated by sort of the application side, but the results relate very nicely to homotopy, to problems in homotopy theory. So I'm going to be spoiling the presentation with these more general results. Spoiling this. Well, not spoiling, introducing new things. Okay, so let me first talk about equivariant topological complexity, which was introduced by Coleman and Grant. And here the idea is that you have, again, your vibration, double evaluation map, but now you have, suppose you have a Lie group, a compact Lie group, acting. The group could be not so specific, but at least that the action is nice enough. Suppose you have such a group acting on X, on a space continuously, and notice that this evaluation map is equivariant. You can have G acting diagonally here or pointwisely here, and this map is evidently G equivariant. Now you would be asking for sections which preserves the equivariancy. Namely, if you know how to move from X into Y, and then you would be forced to know how to move from Gx into Gy just by following the same path, by translated by the action. Okay, so in these terms I can define the equivariant topological complexity of X being the minimal number of being the equivariant sectional category of this map, which is to say the same thing, except that everywhere you see the possibility of putting an adjective about the invariance, the equivariance, you put it. For instance, they are supposed to be open sets which are stable, which are invariant under the action of the group. You want to have local sections which are also equivariant. You have local sections which are equivariant. And then you want these to be sections up to homotopy, but up to equivariant homotopy. The branches of homotopy, each one of them should be also equivariant. So you look at the sectional category equivariant of that map. And that defines this notion. The interpretation is that, which I already mentioned. And you have standard properties like this is a G vibration, and the proof is essentially the same one as in the non-equivariant case. So that this invariant can be defined through strict G sections, not up to homotopy, G homotopy. And notice also that this is a sharper, this is a more elaborated invariant because you are imposing more conditions. The section should have more equipment. So you have a larger number, sees more of the structure. Now, in general, you can, much of what I said, you can extend it to the case, to the equivariant case. Except that you have to do a little bit careful with fixed points. And I'm going to be pinpointing at two places where this happens. For instance, in planning the motion, you better suppose that your space is G-connected, which means that if 2 points in the space are fixed by some elements of a group, then these 2 points should be joined through a path of points which remain fixed under that group. And this is quite easy to see. Suppose you have X, which is fixed under some element H of some group, and the same thing for Y. And then you have your local section. Well, S of xy, which is this path, will have to be S of hx, hy, because of these two equalities. And then the section is supposed to be equivariant, so this coefficient goes out. And if you evaluate at t, you see that this element at sine t, which is somewhere over here, is the same element when you multiply it by h. So the whole curve is going through fixed points, just as x and y were. So you have to deal with fixed points in a nice way. The other thing is, for instance, recall that the category of a space was a lower bound for the TC, And the same thing would happen in the equivariant case as long as you have some fixed point. This is the just standard notation for the fixed points under this action. So suppose you have a point that remains fixed. Then you can do the same business. Namely, you can take this inclusion. Suppose Z is the point that is fixed by all elements in G. Then you can take this map. Since this is a fixed point, this is a G map. And the pullback would then give you a G fibration. And this would be contractible G wisely, G contractible. That's quite easy to see. And therefore you get this inequality, which is essentially tells you that the category, the equivariant category, bounds from below the equivariant topological complexity. Now, I went through fast through here, but essentially the standard definition of the equivariant category is not by collapsing open sets in the environment to a point, because that has to be collapsed J equivariantly, so there is not much of a hope to collapse to a point, but to collapse to an orbit, necessarily. But that's no problem because I said that X has a fixed point. And then if the space is G connected, and you can collapse to an orbit, then take that point and say, suppose, well, this depends on this result. Namely, if you have a G connected space and you have 2 points, so that the isotropy groups satisfy these inclusions, then you have a way of deforming this orbit to this other orbit. And that only depends on taking a path between these two guys and then extending it, sending this orbit into the corresponding orbits until this happens. And details are written in here. I'm going to try to speed up to say some more other things. Okay. Now, here's one interesting thing that I like about this invariant. Suppose, I already said that the topological complexity of a Cartesian product is bounded from above by the sum of the topological complexities. And this invariant has a similar, although weaker, slightly weaker property, namely, suppose you have a vibration. A Cartesian product is a particular case of a vibration. It's a trivial vibration, but suppose you have a vibration which is comes from a principal vibration and with a new fiber. There's a standard a Borel construction for defining these vibrations, G bundles, with structural group G and fiber, some fiber F. So essentially one has a way of constructing these things. And this result says that the topological complexity of the space, of the total space, is bounded from above, by the topological complexity of the base and the topological complexity of X, but not in the, but you have to take there the equivariant, in the equivariant sense. This is a really nice result, which I actually, Mark and I used it in some other paper. And here's a proof of that, and I'm tempted not to give it, to say some more words. I better go slowly. Let's just do some things, even though I do not finish up. So here's the situation. So I better review what the Borel construction is, I guess. So here's the Borel construction. So what I have here is a group acting on E in a principal way. This is a nice action, free action, and with nice topological properties, and it is classified by the universal G bundle. And then, which would be the map from E down to E modulo G. But then I do this mixing, so to replace the orbits in here, which are copies of G, by copies of X. So essentially I do these things. This is the so-called Borel construction that gives you the total space of a map into E mod G with fiber X. And this is the fibration that I talk about, and this is, for that, this is what I meant. Now, of course, notice that you have to add 1 to the topological complexities and you have to multiply them. This is the tricky part. You have to multiply them rather than to add them. Okay. Now, let's give an argument. This is really easy for that formula. Namely, I want to understand the topological complexity of this Borel construction, namely the double evaluation map for the Borel construction. I can do the same double evaluation map, which is equivariant, by doing the Borel construction for that map. Notice that there are 2 maps from this side to that side. For instance, the top one would take the class of u, comma, a path into the path that sends t into u again, comma, gamma t. This is a very natural map. And then you can do the same thing, but only in the endpoints on the middle level. The diagram commutes. You can check quite easily that this is an inclusion. And then notice, and you can take the projection from this Borel construction into the base space, cross it with itself, and notice that you can do again the same thing. I can project into here. I have here a fibration with fiber x times x, and these are again maps. In fact, this is a pullback, because notice an element in here is an element, an element in here and an element in here with the same image in here would be just an element of this sort, because you want that when evaluated the first coordinate here should be the same. So essentially the pullback is that, and then you're all done, because, well, if the topological complexity of the base space is K with open cover like that, well, take that open cover, you have homotopy sections of this form. Now, rho is a fibration. So this is a fibration. The Cartesian plot is a fibration, so that this strict homotopy pullback is a homotopy pullback. Sorry, I don't know what I said. This strict pullback is a homotopy pullback. And here you have a homotopy section, so you can pull it back to a homotopy section. Now you have a way of sectioning this inclusion up to here, and then you can also use the fact that you know what the topological complexity equivariantly of X is, namely you know some invariant domains with equivariant sections, and you can feed it into here to get local sections into here. But of course these open sets might not be compatible with this, so you have to intersect everyone against everyone, and at the end you would have precisely the product of sections for this map, because you have to go into there so that to have a section. And in particular you have section for this guy. That's essentially the proof. And that's quite nice result, but it is, I may not have enough time, but there is another variation of topological complexity due to Dranishnikov that says that is quite close to this one. It varies, it's stronger, has more, takes more of the equipment of the situation, and with a nice property that this formula applies basically essentially in the right situation, namely it bounds from above the topological complexity of the total space of the fiber of the G bundle by the topological complexity of the base plus, not product, the topological complexity is strongly equivariant of the fiber. And that's a very neat thing with connections to the topological complexity of groups, namely of Feynman-MacLane spaces K pi 1s. I'm saying this because I might not have enough time for going up to that point. All right. So actually, before going into, it is natural to talk about, talking about the Dranishnikov strongly equivariant topological complexity, it is natural to talk about the invariant topological complexity introduced by Lubavsky and Marcentowicz, and which arises as follows. So again, you have a group acting on a space, and the idea is, in the equivariance setting, you wanted to plan the motion from x to y, And that should imply how to move from gx into gy. But now I want to be, this is sort of parallel. You want to move from one orbit to the other orbit, but only by moving by the same y, by the same g. So now the idea when using invariant topological complexity is that you want to have two copies of g, g1 and g2, acting on either both on x and on y. And I want to, if I know how to plan the motion from x to y, I should already know how to plan the motion from any point in the orbit of x into any point in the orbit of y. And there is a problem, of course, because recall that the double evaluation map, the domain of that is the paths. And G acts on the paths in point-wisely, but G cross G doesn't. Now recall that the paths is homotopy type of the diagonal, is of the homotopy type of the diagonal, and the diagonal, of course, has an action of G, nothing else. It doesn't have an action of G times G. So what you do is you fatten up the diagonal and do the same business. So here's what you do. You define, this is a replacement, this is a space that replaces the paths. This space contains the pairs of paths, alpha and beta. Think of this picture. There's a path in here and then another path, but the condition is that the point at where alpha ends lies in the same orbit as the point where beta starts. That should be congruent mod G. So in other words, you have paths, but somehow, somewhere in the middle, you can leap it to another point. So that defines the space as a pullback, essentially. This is the space. And then you have a map from a pair of paths with that condition into here, which evaluates at the very beginning and at the very end of the path. And then you've got it away with it, namely you have G cross G acting on two paths. So on two paths which are lifted, like that. So now you have this vibration which is G cross G equivariant, and then you can take the G cross G equivariant sectional category of that vibration, and this is this invariant topological complexity. One can observe that this vibration is G equivariant. This is a vibration, it's quite easy. And the same, it's just as easy to see that it is G equivariant, the same argument essentially. And it's explained over here. So you can define the invariant topological complexity through strict G cross G sections. Now, one property that I find very interesting with this invariant is the fact that the invariant topological complexity is quite related to the topological complexity of the orbit space. And most likely that was the main reason for introducing this definition. Namely, notice that you have here, I have the double evaluation map for the orbit space. I have this vibration that defines the invariant topological complexity. And notice that one has two horizontal maps. Namely, this is just the Cartesian product of the two open maps here. These are quotient maps. And over here, if I have two paths that are shifted that way, when I pass to the orbit space, they are ensured to match together to produce a path here. And notice that this is open. So if I have a local section here, which is equivariant, then I can just continue to here and pass it to the quotient because it's a quotient map, and I would have a regular section for the other guy, which gives me this much of the inequalities. And the result is that if all the orbits have the same homeomorphism type, I guess, then, for instance, if the action is free, all the orbits are G, then the two numbers agree. And or I already said that this is always larger than or equal to that. But they are the same, essentially because of the same diagram that I had before. Now, just as this is a covering projection, this is also a covering projection, and in fact this is a pullback diagram. So, if you take local sections, you can pull them back through equivariant sections. And that's essentially the case, the proof in the case, the most simple case. Namely the one that I understand, where G is finite and the action is free, suppose you have a principal action. So this is very nice. One has one of the main motivations for this invariant. Next. Strongly equivariant TC. The definition, I'm not going to be giving the exact details, but it's the same. Dranichnikov's strongly equivariant TC is somewhere in between. It's a sort of a compromise between the two previous versions, namely Marx's equivariant topological complexity and the invariant topological complexity. It's in the middle. Namely, for the strongly equivariant topological complexity, what you require, you work with the same vibration. You don't split the paths. You take the same thing and you consider invariant open sets with equivariant sections with respect to the action. The only difference being that the sets, rather than being invariant under the action of G, should be invariant under the action of G cross G, which acts on X cross X. That's the only difference. In particular, one has this relation, and it is not quite easy to relate the strongly equivariant topological complexity with the invariant topological complexity because they use different vibrations. But at least you can see that this inequality holds at least under these conditions. So indeed, at least under these conditions, this guy is somewhere in the middle of these two guys. Now, one thing that I find even more amusing, this is Marx and Helen's upper bound that we proved here quickly. And, well, in the case of the strongly equivariant topological complexity, this is what you get. And I'm tempted to say, we can ask, if this was really the main motivation for the introduction of this definition, namely, topological complexity of the total space of a G bundle is bounded from above by the topological complexity of the base and the fiber as long as you take the sum of them, as long as you take the strongly equivariant TC of the fiber. And that's amazingly nice, essentially because, well, if the group G is trivial, of course you have a trivial vibration and you get here, and you recover the product formula. But also it allows you, I'm not going to be proving that result, it's a little bit more technical, but I'm going to be using it for the next topic. Namely, you can use that result to get very nice, sometimes useful, sometimes not, upper bounds for the topological complexity of any space in terms of the fundamental group and the dimension of the space. Namely, suppose you have a path-connected CW complex, take pi to be the fundamental group, and take the universal cover. So this group is acting on the universal cover, this is the orbit space, and you have the universal cover. Now we can look at these two vibrations. Both have this Borel construction for the total spaces. But since the action of pi in this space and at that space is nice in both cases, I can project into either one of those. And in particular, I can project into here, which meaning this guy. So I have a vibration here with fiber, the total space, this e pi, which is contractible. So this is a homotopy equivalence. On the other hand, I can project in the usual way to the classifying space of the group. Now the fiber would be the universal cover, and now I can apply Dranichnikov's result, namely topological complexity of this guy, which is X up to homotopy, and this is a homotopy invariant, is bounded from above by the topological complexity of these two guys, the sun, the regular one here and the strongly Ecuadorian there. Now, one thing that proves Ranisnikov, in addition to all that, is that this guy is bounded from above by the dimension of the space, which is more or less natural to think about, because after all, this is a simply connected space. It starts in dimension 2, and if this were regular TC, it would be bounded from above by twice the dimension divided by 2. So in that sense, this is basically the same upper bound. This is quite believable. But in particular, when you put everything together, you get that the topological complexity of X is bounded from above by the dimension of the covering space, which is the dimension of X, and the topological complexity of the classifying space of this discrete group. And it is a very interesting problem to think about the topological complexity of Eilenberg-MacLane spaces K pi 1s. This is not such a space. The homotopy type of those spaces is well understood to be always the same, and therefore one can define the topological complexity of a group, discrete group, to be the topological complexity of its classifying space. And a very interesting question raised by Farber was to say, okay, what can you say about the topological complexity of a group as an invariant of the group in algebraic terms? And of course the equation is motivated by what happens by, how am I doing? 5 more minutes? Yeah. Okay. This is motivated by what happens about the category of such spaces. Namely, it is well known, it's a result of Eilenberg and Ganea, that the category of such a space is given by the cohomology dimension of this group. Namely, the largest dimension of the cohomology of group with any coefficient where you have non-trivial information, or equivalently the projected dimension of this trivial, of Z, thought of as a trivial Z-pi module. Namely, the length of such the shortest possible resolution. Okay, so in the case of category, the answer is well understood, but what happens for the TC of the group? What can you say about that? And well, first of all, if the group is abelian, then one thing that I learned from Mark, I'm sure of that, is that if the group is abelian, I'm sure not because of Mark has told me, but because I learned it so late. Sorry. The category of the Eilenberg-MacLane space of a group, which is abelian, is an H-space, if and only if, and in particular it's an H-space, so the category is the TC is the category, and that's well understood. So, well, we can just avoid abelian groups. Those are not interesting, well, not so interesting from the point of view of TC. So, avoid those. If the group has torsion, it's also standard that the cohomological dimension is infinite. So the category is infinite, and that's a lower bound for TC, so TC is also infinite. That's not of interest. So let's just stay away also from the torsion, the torsion group. So I better be considering torsion-free groups. And also, if the group was free, well, it's known by work of Stallings and Swan that those groups, free groups, are characterized by having cohomological dimension 1. And since the topological complexity is bounded from above by twice that number, topological complexity can only be 2. And one thing that I didn't say is that it could be 0, 1, or 2. Cannot be 0 because it is not contractible. Cannot be 1 because it is not, well, only one case would be an odd sphere, namely a circle. This is a characterization of U and Lupton. Opera. That only homotopy odd-dimensional spheres have topological complexity 1. So those can be managed. So suppose it's non-free. So now, in addition, there is this very deep result of Eilenberg and Ganea that says that, say you stay with finally presented groups, as long as n is larger than or equal to 3, the cohomological dimension is essentially the geometric dimension of the classifying space. Namely, the cohomological dimension is n if and only if this space has the homotopy type of a CW complex of dimension n, and this is true except for 2. One is not an exceptional case, because what I already said, that's well understood, and well, this is the result. And by the way, this implication is in that direction, from there to here, is always true. Namely, if the dimension is most n, well, the cohomological dimension certainly is bounded by the same thing. But when this is 2, it is known that this will have a topological realization of dimension 3, but it is not known whether it would have to have a realization of dimension 2. And that is known as the Eilenberg-Ganea conjecture, which, by the way, is very deep and might actually be false in case another sort of related conjecture, the Whitehead's conjecture, turns out to be true. Namely, the two conjectures cannot be true at the same time. And Vesvina and Brady proved essentially, well, what is Whitehead's conjecture? Whitehead's conjecture deals with these spaces. Namely, you have a cyclic space, an Eilenberg-MacLane space of dimension 2, then the conjecture says that any subcomplex connected will have to be also acyclic. And that cannot be true at the same time as together with the Eilenberg-Ganea conjecture. So this is really very nice. But then, okay, so how much time do I have? 0. So let me just finish with this example. One example and we're done. Well, I already tried to motivate the connection of TC up to this point, TC of a group. And, well, it's a difficult problem. I'm going to be giving an example of what happens with some sort of nice groups. Namely, this is a result of Dan Cohen and Michael Farber. It deals with right-angle arcing groups and their topological complexity. So these guys arise in the following context. What is a right-angle arcing group? So suppose you start with a graph, gamma. Gamma is a graph. Then you have a group which arises as follows. It's going to have a presentation. The graph is finite, suppose. So it's going to be a finitely presented group. Generators are just the vertices of the graph. Relations are commutative relations between the generators which are adjacent in the graph. That's right-angle arcing group. And it turns out that their classifying spaces arise very naturally in toric topology. Namely, they are spaces which are union of subtori of the Cartesian product with so many factors, and you put one such subtorus whenever you have a clique in the graph, essentially. They are also called, they are polyhedral products in terms of the clique complex of the graph. Anyway, you have these groups and their classifying spaces, and now the category of such a group, namely the classifying space, is just the clique number of the graph, namely the largest possible number of vertices that form a complete subgraph of the graph, of the given graph. So that's combinatorial information. The clique number is combinatorial information, the category of these guys is combinatorial information. Well, but the situation for TC is even more, has a little extra combinatorial information. Namely, it's given in terms of clique, maximal cliques, but it's not just the number, the clique number. You have to take the maximum of these numbers, the size of cliques, maximal cliques, removing common intersections. So let's now finish. In particular, these guys are nice examples, as observed by Julie Rudiak, that will recall that the topological complexity is bounded from below by category and by from above by the category of the Cartesian product, and any situation in between can happen, essentially depending on whether maximal cliques overlap or not. So let me just stop there. I was going to talk about another versions of symmetric TC in relation to immersion problems, and there's a bunch of nice results with connections into homotopy theory and some applications into some discretized model that I was going to talk about. But I guess the conclusion is this vivid area may not be so applied, but it's beginning to be so. So thank you very much.
Are there any questions? Well, I have one. So I understand the applications, or kind of understand the applications to robotics of TC. But you talked a lot about equivariant TC and so on. And is there something kind of coming out in terms of applications to robotics and whatever else of equivariant?
I don't know if it is coming out. I'm not working on such applications currently. It would be, it's kind of easy to cook up examples, artificial examples from robots or stuff like that, but who knows? This is kind of mathematics that has a applied language, and all of a sudden might be relevant in actual industrial applications. But to tell you the truth, I do not know any concrete applications. I've worked some discretized model of TC, which is has the characteristic that you can implement it into a computer and do search. Well, if you have enough time and enough compute resources and a good strategy, but for finding optimal motion planners, or at least safe motion planners, which might be useful in concrete applications. But other than that, I wouldn't know.
Thank you. Any other questions? Well, if not, then let's thank Jesus again.